Hello everyone. Today we are going to talk about equilibrium of a rigid body. Whenever we are talking about equilibrium, means there is no motion. So summation of forces is equal to zero. And because we are talking about a rigid body, we are not neglecting the dimension. So summation of moments is equal to zero as well. For equilibrium of a particle, we didn't have any moment because dimensions were negligible. But here we have another set of equations, which are the moment equations. So to solve equilibrium problem, the procedure is very similar to equilibrium of a particle. The first step is to draw a free body diagram. And to draw a free body diagram, we have to remove all the supports. When we are removing the supports, we have to include the loads that are being applied by the supports. Then we are going to show all the forces and moments acting on the body. Sometimes we group forces and moments and call them loading. And then we are going to label all the known and unknown forces. Forces and moments, so I'm going to group them and call them loading. And their direction. So that's the first step. Whenever we are talking about equilibrium, first we have to start with free body diagram, similar to equilibrium of a particle. Then we are going to write equations of equilibrium. So equations of equilibrium, if we are in two-dimensional, we have summation of forces in x direction equals 0, summation of forces in y direction, and moment, summation of moment would be equal to 0. So in two-dimensional, we can write a moment equation about any point of interest. Let's say I'm going to write it about point A. Or alternatively, I can write about point B. If I have a beam, and then with different loading acting on our beam at point A, at point B, let's say at point C, I can write a moment equation about any point. But we usually write a moment equation about a point that we have more loading, so we can get rid of some of our loading when we write a moment equation about that point. But remember, in 2D we only have 3 equations. No more. This, if we write a moment equation about multiple points, it's not going to give us additional equation. They're linearly dependent. So we only have 3 equations. So summation of moment in 2D when we are having x and y, basically summation of moment is about the z-axis. That's what we are dealing with in 2D. And in 3-dimensional, we have summation of forces in x direction, summation of forces in y direction, summation of forces in z direction, and then summation of moment, which in 3D is easier to use the moment definition, the vector definition of r cross f. And this will give us 3 components. The result of r cross f is a vector. So we have I component, j component, and k component. So basically we have 3 equations, or you can think of it as x-axis, y-axis, and z-axis. So at the end, I will have 1, 2, 3 4, 5, and 6 equations. So in 3D equilibrium, I can solve for 6 unknowns because I have 6 equations. And in 2D, I can only solve for 3 unknowns because I only have 3 equations. So a very practical example of summation of moment equals 0 is a lever. So when we are using a lever, if you are applying load here, let's call it F1, because we are dealing with equilibrium. So let's say there is a weight here being applied. The moment about point O should be the same. So summation of moment should be 0. That means that F1 times D1, if we apply a small load, but if the distance D1 is high, then we get a large moment. And if the distance D2 is small, then W has to be large. So the weight that this lever can lift is simply F1 D1 over D2. And if I want to give it with an example, if you're applying, let's say we can apply 150 pound, and the distance is 10 feet here, and then here is only, we place it at 1 foot. So the W, we want to see if we apply 100 feet at 150 pound, how much load can we lift? So that would be 10 divided by 1, that would be 1500 pound. So we can see a simple lever can lift 1500 pound if you're only applying 150 pound. So that's the power of a moment. The force is much lower than the force that we want to lift. Let's look at an example of finding the reaction moment, forces and moments. So in this example, we want to find the reaction forces and moments. Let's say we have a cantilever beam, which means that one side is fixed, the other side is free. I call this point A, and this distance 5 meters, and let's say we are applying 50 Newton. The first step is to draw the free body diagram. So in this free body diagram, we have to remove all the supports. Here we have a clamped. In clamped, it doesn't allow our beam to move in X, Y direction or have any rotation. So we are going to have reaction in Y, reaction in from X, and the moment A. So there is a separate video about how to find the reaction forces for different supports. In that video, we discuss why a cantilever beam has 3 reactions and a simply supported 2. So 50 Newton, and this distance is 5 meters. So this is a complete free body diagram. Now we have 3 unknown, AX, AY, and MA. They are the loading at point A. And I can write 3 equations to solve for these unknown. Summation of forces at X equals 0. And let me draw my coordinate. This is X and this is Y. The only force that I have is AX. So that means AX is 0. Summation of forces in Y equals 0. I have AY and I have negative 50. Therefore, AY would be 50 Newton. And if I write summation of moment about point A equals 0, I have to assume the positive direction. As always, the convention is counterclockwise is positive. Therefore, if I write the summation of moment about point A, I have my moment MA, but the forces AX and AY are not creating any moment about point A because the moment arm is 0. So the only force that is creating a moment is that 50 Newton, which will try to rotate our beam clockwise. So it's negative. Magnitude 50, moment arm is 5, equals 0. Therefore, MA is 250 Newton meter. So we found the support reaction. We had 3 unknown, and in 2D we have 3 equilibrium equations, so we could solve for those 3 unknowns.